Hi, in this video, we're going to take a look at preparing our data for classification supervised learning models. All right, so our goal here is that we have a binary category variable that we want to predict, or we want to have a control over, or we want to do for inference. So, these are the major aspects of supervised learning that we typically use our models for. Most of the time, we're trying to predict, the future. But it might be that we want to do like classical statistics inference. That's another possibility. Or another possibility is I have something like an assembly line where I want to control the output, and I'm using my model to understand how I can change the variables to get the output that I actually want. Okay, so here we have two levels of our target variable. We're going to be using a mushroom data set from Kaggle, and we have poisonous or edible. Okay, and so let's go ahead and dig into this. All right, so first thing I'm going to do is I'm going to import the necessary libraries. So I'm going to use pandas to set up my data and do a lot of my data manipulation, NumPy for mathematical computations, and OS, I use this to make sure I know where I am on my computer. I always do this at the beginning of my code, where, just so that I know where am I currently located inside my computer as I do my work. All right, so now let's go ahead and load my data. All right, so I'm going to use read CSV. Now, my understanding is that PyArrow is a faster way to read CSVs. And if I know my data type beforehand, it's best if I go through and say what the data types are. And so I'm just saying, hey, put in everything as a string. And I'm going to impute missing values as NA. Notice I put n/A for missing values. What this does, this sets it up so that when I have a missing value, it's consistent with how Excel will treat missing values. And I find this is a good approach for my stakeholders. Okay, so let's take a look at what does our data look like. And so here, this is just the first 5 rows of data. And our goal is to say, hey, is this mushroom edible or poisonous based off of the features that we see? So we have the classes poisonous or edible. We have cap shape, cap surface, cap color, bruises. Now odor. Now for me working through this already, I know that odor is a super powerful predictor variable. And I'm going to show you a phenomenal model basically because this one column is really, really good. The model I'm going to show is phenomenal. It's an excellent model. And really the reason for that is that kind of like in poker, I've been dealt 4 aces. If you're dealt 4 aces, it's hard to lose. Just don't mess it up. Basically, with this data set, class and odor is you almost have a perfect model just off of odor alone. All these other variables we could get by without more than likely, but here I'm going to show you the full process as if I didn't have such a powerful feature already available. I'm taking the point of view that this is a new project. I don't know what's in my data, and I don't have a predictor variable that is as powerful as odor. All right, so now let's look at our target variable. Okay, so here we can see that we have a little bit more than 50% are edible and just under 50% are poisonous. And so, 52% are edible, 48% are poisonous. Okay, so now I always visualize things. Here I use a bar plot, and so I'm using matplotlib. And so we can see, here we have the counts of poisonous, the counts of edible in our data set. Okay, so what I'm going to do, I'm going to prepare my data for my supervised learning. And I always want to keep my original data intact, and that way I can always go back to it if I need to change something. And so here I'm going to make a copy of my data. And what I'm going to do to be able to do the binary classification I'm going to do, I'm going to switch my target variable class to zeros and ones. 0 if it's edible, 1 if it's poisonous. Okay, and so this is a more common way for supervised learning software to handle classification, to have zeros and ones. So I'm going to do that here. This also gives me the advantage that when I look at averages by different predictor variables, I can just take the mean, and I'll be able to get the percentage or the fraction of poisonous very easily. All right, now I went through the data and I saw that veil type is a constant column. It's constant. That means it has no informative value. So for this purpose, I'm going to remove it from my prepared data. Now you'll notice that I keep it in my original data set, but I don't remove it from my prepared data. Now, what I'm going to do, and this is how I proceed at work, I'm going to list out all of my predictor variables into a list object. Typically, what I do is that I'll have a list for the ID variables I have, list for the date variables, list for numeric predictor variables, a list for categorical predictor variables, a list for like partition variables, list for like administrative variables, and I keep everything very well organized, so that way I know like I could just like grab onto the list to get everything together. Why do I do this? Well, when I do my data prep, if I need to, manipulate and change things, typically numeric predictor variables get prepared the same way across the board. Categorical will get prepared across the board largely, and dates will get prepared the same way. And so by having a list, I can automate the process in a for loop very nicely, which I'm going to show you in a moment. All right, so now what I'm going to do with this, so all of these are categorical. Honestly, if I was at work, I would call this list categorical instead of list predictors, but all the predictors are categorical, so I just call it predictors. All right, now what I'm going to do is I'm going to take a look at the association between my target variable and my predictor variables, okay? And so to do that, I'm going to go ahead and create a contingency table. And with that contingency table, I have the rows are going to correspond to the covariate or the independent variable values, and the columns are going to correspond to poisonous or edible. Then once I have that, I'm going to compute Kramer's V. That's actually the default association analysis in the association function from SciPy. And so I'm just going to go through and get all of the Kramer's V values. And now Kramer's V goes from 0 to 1. And we can think of it as, now classically trained statisticians will hate me for saying this, but we can think of it as like correlation, but for categorical data. It's not 100% right. It's more of an association measurement, but you can think of it, very similar to correlation. But remember, it goes from 0 to 1, not -1 to 1 like Pearson's correlation does. All right, and now what I'm going to do, I'm going to sort the predictor variables by Kramer's V, so that I have large ones first and lower Kramer V values last. And so what this is going to do for me, this is going to make it easy for me to know more than likely which variables are going to be the most useful when I do my supervised learning. And so we can see odor is coming out with a 0.97 Kramer's V. All right, that's really, really large. And so like just out of the gate, if I just use odor and no other predictor variables, I'm more than likely going to have a good model right out the gate. And I can scroll down and look at the rest. All right, so why do I do this? Well, this sets it up that when I do my feature selection, which we'll talk about in future videos, when I do my feature selection, I'm expecting to use these variables up top, and I'm expecting to not use these. And so as I go through and do my feature selection, I'm going to be prone to removing the ones at the bottom. I'm going to be prone to keeping the ones at the top as I work through this. All right, so now I'm going to go through, and to better understand my data, I'm going to plot my target variable by my predictor variables. All right, now typically this is part of the process of presenting what we're going to do to my stakeholders at work, to make sure that they understand what's going on, to make sure that they feel comfortable with the data, that the data is consistent with what they believe, because if it's not consistent with what they believe, there might be a problem with the data, and I don't want to proceed. Also, good visualizations that your stakeholders understand will make your stakeholders have more faith in you. And if they have more faith in you, you're going to have an easier time getting your project accomplished. All right, so now let's go ahead and look at the actual plots. So here, So you'll notice that when I look at odor, I have, practically speaking, it's either all green or all red on my bar plots. Here, when I look at N, there is a difference. But if it's P, S, Y, F, and C, they're all red. If it's A and L, then they are all green. Okay, so this is why it's such a it looks like it's going to be such a powerful predictor variable. Now, when we get down to here, we have our spore print color. And we can just like go through and just see what the differences are. And so this is the second highest Kramer's V value. Now we got our third highest Kramer's V, and I can just keep on going through and scrolling down. Something that I would have done if this was for work, I would have actually ordered these by the total count so that I have the category with the highest levels first going to the lowest, the most frequent to least frequent. And then, we can just keep scrolling through, looking at this. And as we get further down, we're going to notice that the red and green bars are going to start looking more similar to each other. They'll have more similar heights progressively as we scroll down. That's because of the Kramer's V calculation that I did, that I sorted them in this manner. And as we keep on going, so like now you can see that this bar, the green and the red, are really close to each other. There's a little bit of a difference. I mean, this is negligible, so few ends. Now, things are starting to look very, very similar in terms of the height of the red and the green. And so like here, there's very little distinguishing ability between these. So if I see T for stock shape, there is a slight better chance that it's edible than poisonous. If I see a stock shape of E, it's slightly more likely to be poisonous than edible, but it's not a strong signal in there. This is not as good of a predictor variable as odor is going to be. All right, so now let's talk about preparing our actual data. Okay, so there are some problems with these predictor variables. Categorical data needs to be converted to binary columns for scikit-learn. Now, they don't have to be for certain model types and other softwares, tree models in particular, and in like Enterprise Miner, we don't have to convert over to binary columns. But scikit-learn, we have to, and I'm working in Pandas, or I'm working in Python. So I'm using scikit-learn, and this framework says that all predictor variables must be numeric when I fit my model and when I make my predictions. Therefore, I have to convert my categorical data over to numeric, some way, some shape, some form. The typical way to do this is that for each level, we're going to have what's called a dummy variable of zeros and ones. So stock shape will correspond to an E column that has a 1 if it's an E, 0 if it's not, and a T column that'll have a 1 if it's a T, 0 if it's not. So this one predictor variable is going to result in 2 columns. GIL attachment will have 2 columns. Now notice that GIL attachment has very few values. This is a problem also because here, this A column is almost all zeros, while this F is almost all ones. Now, veil color is going to result in 4 different columns, and you'll notice that we have very few N, O, and Y values. So these 3 columns are going to end up being very sparse, not very useful. And so it's unlikely that these would be helpful in my model. By having unnecessary predictor variables, I'm more prone to overfitting. It's going to take longer to compute to fit the model and to score data. It's going to be harder to interpret. And so it's going to take, I'm going to be more prone to overfit. It's going to be harder to interpret. I'm going to have a bunch of like useless gunk, clogging up the system. And it's going to take a longer time to compute. And so these are disadvantages. So I don't want to have unnecessary columns. I only want column predictor variables that are useful in my modeling process. So what I'm going to do is that I'm going to choose a strategy to prepare my categorical data. All right, so here I've listed 4 different ways. First one is to bin by using subject matter knowledge. So let's say that my target variable was like weather, and I had state as a predictor variable. Well, I could put Georgia and Florida together because they're adjacent to each other. They're likely to have similar weather. Now, if I was dealing with finance, though, well, Georgia and let's say Alabama and Florida, they're adjacent to each other, they neighbor each other, but Alabama and Florida have very different economics. And I would not want to put Alabama and Florida together if I had an economic problem because they're just very, very different in this manner. And so I want to use subject matter knowledge of knowing which levels are very similar to each other and group them together. Also, I could, group levels together that have the, similar averages, similar bar plots that I just showed. So if one level has like a 50% poisonous, another one has 51% poisonous, I might want to put those two together because their percentages are so similar for poisonous. Now, we could also do binary binning. This one is really just binning by average, just a little bit faster, a little bit easier to do. Here we say that we put down a 1 if the categorical average is above the overall average and 0 if it's below. This is very fast. This is the one that will expose me the least to overfitting. And then the next one is categorical smoothing. Now, this one is not liked by a lot of classically trained statisticians. Here, what I'm going to do, I'm going to replace levels with their average value. So what I would be doing here is looking at this bar, N would get replaced with approximately 0, O would get replaced with 0, Y would get replaced with 0, and W would get replaced with approximately 50%. And so this gives an easy way for us to convert over, and that's called categorical smoothing. Binary binning and categorical smoothing are not going to increase the number of columns I have, and so these are the ones that are going to make me the least prone to overfitting. The more columns I have, the more prone to overfitting I am. Now, the one that I'm going to do is I'm going to bin by average target variable. I'm going to choose to bin into 3 groups. It's going to work out that potentially, from a potential point of view, a predictor variable has the greatest potential for being informative if its levels are approximately equal across the board. So that's saying if I have 2 levels, 50-50 is going to be potentially the most informative. 3 levels, 1/3, 1/3, 1/3 is potentially the most informative, and 4 levels, 25% each, is potentially the most informative, and so on. Typically at work, I go with 20% for 5 different levels. That's usually what I do because that's what my boss prefers. Here, I'm going to do 3 levels just to make it as simple as possible because I'm not doing binary, so I'm doing, 1/3, 1/3, 1/3. Now, something about this, I am not going to get perfectly 1/3, 1/3, 1/3. It's going to be close, but it's not going to be exact. Here, what my goal is to improve each categorical predictor variable to be as powerful as possible, and then use that in my supervised learning. Binning is our most important tool for preparing categorical predictor variables. And so my game plan is I'm going to take levels that have a similar percentage of poisonous and put them together where I try as best as I can to get my levels grouped up into approximately 1/3, 1/3, and 1/3. All right, so here I've wrote the code to do this. And so now let's take a look at odor. All right, so now odor, I've got L, A, and N are going to be binned into one group. Y and S are going to be another group, and then P, M, F, C are going to be in another group. Now, what's going on here is that L, A, and N are all in the low category. Y and S are in the moderate, and then P, M, F, C are all in the high. Now, if I look at my percentages, so 3%, practically 0, 27%, and 2%. So here, high is about 32% of all my data. Now here, when I look at low, this is over 50%. Okay, so this big chunk right here is going to make it so that no matter what I do, I cannot get 1/3, 1/3, 1/3 because of that 43% right there. Now, when I look at this, N has an average of 3% poisonous. All right. Now, when I look at A, it has 0%. L has 0% poisonous. All right. So where am I going to put it in the group? Well, I want my goal with this, my plan of attack is that I want to have similar percentages for my target variable. I want target variable averages to be very similar to each other. You'll notice that when I look at very high, they all have up to rounding 1 for the average of poisonous. And so now it works out that Y and S also, I could, I could have just put it into one group because we have the same class average. This typically doesn't have it happen. When I'm normally doing this, like if I'm doing this on like, let's say a state, across the United States, there's more of a gradient and there's a smoothness here. Now, how I achieve working this out is that you'll notice I take the levels of the predictor variable, I order them by the average of the target variable, and I compute the counts and the proportions. And then I, go through and I cut. And how I do this cut is I do like an ascending, descending trick. Ascending is I take the cumulative proportion as I go down like this. Descending is I go 1 minus the cumulative going the opposite way. And then I take the average of the two. And so here I'm taking the cumulative of the proportion as I go down the list here. Here I'm taking 1 minus the cumulative as I'm going up. Notice that I did reverse the order. And then I take the average of those two. I find that this is the best way to handle these big chunk values going on. And then I run through this. I do this for all the different predictor variables. Now notice here, I only have 2 levels. I could have honestly just, convert this over to binary directly, where it's 1 if it's N, 0 if it's B. That's effectively what's going to end up happening anyway when I do my dummy variable conversion. But here we see that half of it is in this one group. There's no way I can get 50-50. And so you can see all the low ones, low classification percentages are all in the same group. And we scroll through, and this is part of the process of of building models, is making sure everything looks like coherent and sane. And so now we get down to stock shape, and we can see that it's pretty close to 50-50. This is not going to be a very helpful predictor variable. All right, so now let's look at what does our prepared data look like now. All right, so remember these are all categorical variables. Now I went with 1 low, 2 moderate, and 3 high. The reason why I do 1, 2, 3 like this is first and foremost, the order matches to low, medium, and high for the classification. Now, it's still categorical data. I don't want to mistake it for numeric data. It's not numeric data, so I don't want to treat it as if it was numeric data. So I'm not going to put 1, 2, 3. I'm keeping it as a category, and so I'm doing low, moderate, and high. So it's ordinal data. All right, so now let's do the bar plots again, but now let's do it with with our prepared data. And you'll notice now odor is much simpler. I've got 3 bars, 3 levels. Now, one thing that is nice about this is that it's easier to interpret. It's easier to understand what's going on in terms of interpreting, the relationship between the predictor variable and the target variable. But now I've lost the information of going back and forth. What I typically do at work is that I actually build out these data frames, and in my data prep, I actually have in my code explicitly saying what the groups are line by line, and then that way, if someone looks back at the code, they see exactly what the crosswalk was. All right, and so we can scroll through this. We can keep on going down. And so let's get to the bottom. Let's go to all right, so like here, veil color, we can see that here, this is nearly 50-50. We have low and high, but these are so rare that they're not going to be that useful, which is consistent with the Kramer's V point of view. And so here, there isn't much of a signal here. There's a little bit of a signal if it's low, but this overall, this predictor variable is not going to have a big impact on what's going on. All right, so let's go ahead and convert over to dummy variables. So what's going to end up happening is that for each level of the of each categorical predictor variable, I'm going to end up getting a column of zeros and ones. And so here, after I do that, so how I do that is with get dummies from pandas. And so odor has C, odor has F, odor has L. I'm doing this with the raw original data. This is the original data. When I do it here, I'm doing it with the prepared data. And so here I can see what were the original levels. Typically at work, I don't need to do that. Typically at work, I'm not going to do this one step. I'm doing the raw data to show you what it would look like if I didn't do my categorical data preparation. And so, we can see all of these. Now, what I want you to notice is how many more predictor variables do I have than I have here. All right, so here I've bent things together. I've collapsed groups into fewer groups. And so and hopefully if I've done this in a coherent manner, I'll actually have better predictor variables in this version than in this version of the data. Look at how many more I have in the raw data than I have in the prepared data. All right, the more predictor variables I have, the more prone to overfitting I am. The more predictor variables I have, the harder it is to interpret. The more predictor variables I have, the longer it's going to take to fit the model, longer it's going to take to score my data. All right, so now let's partition our data into our train validation test split. Now, the convention in scikit-learn is that I grab an object for the model I want, and then I fit it separately. So I have an object, and the reason why we do it this way is that if I want to fit with different data sets and change things up, I have this flexibility. This makes it easier to do that. And so, like if I want to keep this aspect of the function the same across different training data sets, I can do that, and I can change up my training data very easily. This is a very nice approach. All right, and so here I'm going to fit the model. Now I'm going to use this penalty equals none. What this is doing is that this is saying I want classic logistic regression. The default is to do L2 norm fitting. All right, what that does is that will shrink less useful predictor variables to have very small coefficients. All right, and so here I am using the raw data. Here I'm going to use my prepared data. Now let's go ahead and predict what's going to happen. So here I decided to store it in a prediction data frame. I have the original class value. I have the raw model predicted, the prepared data model predicted, and I have the partition. And this is an easy way for me to go through and grab and evaluate my train validation test statistics. And you'll notice that when I check that, my train, my validation, and my test are very, very strong. All right, so the training data, this is the data that I build my model with. Validation is used for fine tuning and final model selection. Test is is how I go through and get my honest estimate of how the model will perform in the future. Now, the situation here is that odor is such a powerful predictor variable. This is like being handed 4 aces in poker. It's hard to lose when you're handed 4 aces. And it's possible you can mess it up. It's unlikely, but here I've been handed such a nice data set that my model is super, super powerful. Here, we're not going to see a meaningful difference between our prepared data and our raw data on this one. Trust me, larger data sets, other data sets, typical data sets, it's going to be a big difference. You'll get a better result if you do your categorical data preparation. All right, well, that's all I've got for you. Oh, homework. So I didn't put the homework in. take your data and take your classification data and fit a statistic regret or and pair your let's make it. All right, so now let's view. All right, well, that's good. All right, that's all I've got for you. Life is short. Do math.